Hey math kids, let's finish up this last example for this section. So particle P moves in a straight line with this velocity function. It's given in meters per second. Notice that your book does meters seconds to the -1. That's the same thing as that. So just keep that in mind. So it says find the time when P reverses direction. And so since velocity includes direction, if we have positive velocity, we're going forward. If we have negative velocity, we're going backwards. Since that's the case, all we have to do is t-factor this to find out where it's equal to 0. And we end up with t minus 1, t minus 2, which gives us t is equal to 1 and t is equal to 2. So those are the two roots of that function where it crosses the x-axis, and that tells us where we're changing direction because we're changing from either positive to negative or negative to positive. Now part B says, hence find the distance P travels in the first 4 seconds of motion. And so what we're going to do now is we're going to look at the antiderivative of this because that's going to give us our position function or our displacement function. Okay, so we take the antiderivative, t to the 3 over 3 minus 3t squared divided by the 2 plus 2t plus c. Okay. Now, we're going to assume that the initial displacement is 0. And so if we look at s of 0, we're going to plug in zeros for all of this. So it's just equal to c, where c is 0. Because we're basically saying, I'm going to write that out actually. So what I'm doing is I'm plugging in the origin, because we're assuming that that's where this stopped. Oops, that's a 0. Okay. So that just goes to 0, goes to 0, goes to 0, so c ends up equaling 0. Okay. So this basically just goes away, and this is our function that we can use for the rest of it. But we know that s of 0 equals 0. That's an important thing. Now s of 1, we're going to plug in a 1. So we get 1 cubed is just 1. 1 squared is just 1. 1 times -3 is -3. And plug in a 1 right here, we get a 2. Now, if I go through the process of doing this, that's just going to be 5/6. So s of 1 is 5/6. Okay, s of 2, plug in a 2 for all of this, so 2 cubed is 8. Plug in a 2, we get 2 squared is 4. 4 times -3 is -12. And then we're plugging in a 2, and so that becomes a 4. If we go through common denominators and everything and combine those, we'll end up with 2/3. And if you want me to go over that in math lab, I'm happy to go through that. Okay, and then S4. So notice we chose S0 because that's the beginning point, S4 because that's the ending point, and then S1 and S2 we change directions, and so we care about those points as well. We don't care about S of 3, because of this 1 and 2. We don't care about S of 3 because there's no direction change and it's not an endpoint. Okay, now we plug in 4, so that's 64/3. So 4 cubed is 64, minus 3 times 4 squared, so that's 16 times 3, so what is that, 48 over 2, and then 2 times 4. Once again, if we use common denominators and figure that out, we're going to get 5 and a third, or 16 thirds. Okay. Now, if we make a motion diagram of this, it's going to look like this. So initially we start at 0. And we are, let's see, start at 0, and then we go to, we have 2 thirds is a point, we have 5/6, which is a point of interest, and we have 16 thirds, which is also a point of interest. And so we go forward until we get to 5/6, which is our first direction change. And so we turn around until we get to 2 thirds, and then we turn around and we go all the way to here. Okay. Now, this happens at t equals 1. This happens at t equals 2. And then this is our end point at t equals 4. And then this is our beginning point at t equals 0. So that's our motion diagram. Now, what we need to do is we need to take the distance from here to here, add it, then the distance from here to here, and then the distance from here to here. And so let me get some more room. And so from here to here is 5/6. And then we add that where we take 5/6 and subtract 2 thirds. That's going to tell us the distance from here to here. And then we're going to add that to the distance from the endpoint, 16 thirds, minus 2 thirds, which is the distance from here to here. And so if we add this length plus this length plus this length, that will give us our total displacement, which your book writes it as this. Once again, you'll need common denominators and add them all together. If I was doing that, though, I probably wouldn't change it to a mixed number, so I would get 25, 26, 27, or no, 15, 16, 17. 17 thirds is probably the answer that I would end up with. And remember, that's displacement, so that would be measured in a length, which is our meters. Okay, and then they wanted us to check it against the answer we get. We go from 0 to 4 of this function. So if we go from 0 to 4, and so I'm going to take this thing and evaluate it from 0 to 4. If I plug in 0, though, all these go away. So I really just need to evaluate it at 4. And so if I just plug in, let's see, I think I just need to zoom out is really what I need to do. And so I'm plugging in a 4. And let's see. So we do that, minus 3, 4, plus 2, 4, and if we do this, we'll simplify it. We'll get the same thing we got right here, which is 16 thirds. And so that represents the total displacement, or how much it would be if we didn't really, we kind of looked at the beginning and the end, but we didn't look at the stuff in between. Okay, so that's, so the total distance, so when we go right, left, right, counting all of that length, is this. But if we just take the integral, it's only going to tell us from 0 to here, and we don't really care what happened in between. We kind of look at the beginning and the end. We see the total distance like change from the beginning to the end. And that's pretty much it. So once again, this is called the displacement, and this is called the total distance. Okay, if you need additional help, come to Math Lab and tell them calculator.